So, in this video, we are going to deal with the Nobel Prize in Physics for 1911, awarded to Wilhelm Wien for his discoveries regarding the laws governing the radiation of heat. And in this video, we will deal with his Nobel Prize lecture. There's an earlier video which deals more with the general information, some biographical information, some work-related information, and the award ceremony speech what was given to him. And this lecture is given by him. You see colors of a black body. When it's heated, it gives off radiation of all wavelengths and frequencies, but not all as much. You see here's wavelength, and here's the strength of the light that's coming off the black body. You can see that here the peak is a 500 nanometer wavelength, and that depends on the temperature. This is the sun, by the way, and you can see it is 500 nanometers. That is yellowish, so that's about right. You see another version of that law illustrated. Temperature and wavelengths. Well, you can, if you want to study it more detail, you have to pause the video and you can read information that's given here. Now we'll go on to the Nobel Prize itself, which is titled On the Laws of Thermal Radiation. It is summarized by me. It was not a very, very long lecture. It is not summarized very much. When one leaves pure thermodynamic theory, one faces difficult obstacles. It was possible, that's for Wien of course, and here sends me to derive general law of radiation, the so-called displacement law. Doing this, we had to make use of ideal processes, mental experiments that nevertheless lead to reliable results. This can only be done with processes which laws are known. In this idealization, one must also ignore secondary phenomena. In mechanical heat theory, this has been very fruitfully done by Helmont, Sonthoff, and etc. The conclusions they drew were in agreement with experience. More details and examples I have skipped here. If you want to have all the details, you can also go to the lecture itself, of course. There's a link in the video later and also in the description of the video. Kirchhoff used an ionized cavity surrounded by bodies of equal temperature, and the radiation energy is then independent on the nature of the body. If an aperture is made in the walls surrounding this cavity, this radiation coming out is independent of the nature of the emitting body, and it only depends on the temperature. The same radiation will be given off by a complete black body. This theorem is valid for almost all luminous processes. The temperature concept applies to all luminous processes. Boltzmann directs the law, earlier empirically formulated by Stefan, the Stefan-Boltzmann law, that the radiation of the black body is proportional to the fourth power of the absolute temperature. Here you have the radiation intensity, here you have Boltzmann constant, and here you have the temperature to the fourth power. Color in radiation is also linked to temperature. Use idealized white bodies reflecting all radiation and imagine a black body rating inside the small white body. The radiation will exercise pressure on the mirror walls. This pressure can be calculated. The pressure will expand the bodies unless work is done, which is also be converted to radiation. The walls are moving, so a color change occurs due to the Doppler effect. This change in frequency can be calculated. Later they found that pressure due to light really exists. Arrhenius used it to explain comet tails. The change in the radiation by compression in the space of mirror walls is the same as that is caused by raising the temperature. We can calculate the change of the wavelengths due to the compression and due to the temperature change. The product of the temperature and wavelength remains constant. Here you have the wavelengths times the temperature is a constant, the constant of Wien. If one knows the distribution of intensity of thermal radiation for one temperature, then one can calculate them for all temperatures. When the temperature changes, so does the wavelength with the highest intensity. Lorentz, starting from the Maxwell equation, has derived this displacement law. The law can be used to calculate the temperature of the Sun. It is between 5030 and 6690 degrees Celsius, based on the measurement of wavelengths with the highest intensity. Another application is the calculation of wavelengths of X-rays, Röntgen rays. Electrons hitting bodies create X-rays. The wavelength of the X-rays is a function of the velocity of the electrons and thus of the kinetic energy. The electric energy of the X-rays can be used to calculate their wavelength. The results comply with the wavelength determinations with other methods. The manner in which, at a given temperature, the intensity is distributed over the individual wavelength cannot be determined from thermodynamics and tell us about the specific heat of gases. The kinetic theory of gases based on probability calculation has made progress more than the theory of radiation. The statistical theorists set itself the task to account for the laws of thermodynamics. Whether or not it will be able to do so is a question for the future. Success is achieved. Wien describes it, which I have skipped here, but there's a lot still to do. Wien has made a first attempt with a certain success. Gradually used another approach, starting from the uniform distribution of energy over the degrees of freedom of a system in a state of statistical equilibrium. Radiation can be represented giving a number of degrees of freedom. Analogically, a vibrating string can execute a number of individual vibrations whose half wavelength must be equal to the length of the string divided by an integer. Thus the length of the string divided by an integer is a half the wavelength. The individual standing wave correspond to degrees of freedom. If we allocate to each its proper amount of energy, we get Rayleigh's radiation law. The emission of a wavelength is proportional to the absolute temperature and inversely proportional to the fourth power of the wavelength. Here you see that formula. This is the V, that is the emission, depending on the temperature, and you can see a 2, a constant, another constant, the T, that's the temperature, and the wavelength to the fourth temperature. But you see, you must divide, dus inversely proportional to the fourth power. It agrees with observation at the point where the law above failed. Lorentz derives Rayleigh's law from electromagnetic theory. It contradicts all experiments, because it states that it must be accumulated at shortest wavelength. Thus, with these laws, there are major difficulties. It is clear none of the models that is only based on pure electromagnetic principles can lead to correct results. Planck introduced new hypotheses to avoid Rayleigh's law. It must replace this and my law. Planck retains the distribution of energy over the degrees of freedom starting point. He introduces that the idea that energy divided is rather large quantities, discrete, which cannot be divided. The quantum hypothesis is that. This would have been accepted if it was matter, but it is energy. If we accept it, we arrive at an entirely different distribution of energy of radiating centers. If we introduce energy elements, we relinquish the electromagnetic laws. It seems to Wien that the Planck oscillator does not explain anything. Any doubts whether they can probably be used to establish the relation between energy and emission. According to Wien, de Beyer has shown that the Planck oscillator can be done without, still being able to get results which agree with the laws of radiation. Planck has reformulated his theory, now assuming emission can only occur by whole energy elements. Some problems are solved, others are not, make a further progress hypothesis necessary. There are large difficulties in radiation theory, but one must pay tribute to the achievement of Planck's theory, agreeing with the observed data, including Rayleigh's and my formula, throwing light on different subjects like specific heat. It has been shown that specific heats do not strictly obey the Dulac-Petit law, that they decrease at low temperatures. This law says that in solid bodies every atom has 6 times the energy of a degree of freedom. Einstein derived using Planck's theory elements, quanta, and got a formula for the specific heat showing the drop of temperature and using Planck's oscillator. Again, difficulties. Hence, observation disagree with Einstein's formula. Still a step made by Planck. Difficulties with radiation theory also occur in Einstein's approach. Investigation energy fluctuation even in the state of equilibrium as a result of irregularities of the thermal processes. The fluctuations can be derived from probability calculations. Boltzmann theory states that there is a simple relation between entropy and probability. The entropy is a constant times B, and here you have the probability, the gamma. This is natural logarithm. Is it English? I think it is. The entropy is known from the radiation. The probability of state is also known, from which fluctuations can be calculated. The mathematical expressions contain two factors, one which dominates with high intense radiation, as in Rayleigh's law, one which dominates with low radiations, as in Wien's law. Wien, in the end, states that probably means, stating also it is impossible to introduce a dualistic approach into optics. Assuming Huygens, wave-free, and Newton's emanation theory, we must give up Boltzmann's method of applying calculation to this type of fluctuations or introduce a new irregularity into radiation. Opinions on what to do differ greatly. To Wien, all the deviations from current theory are due to events within the atom. No atom link what is going on inside, and an atom links up with the present theories. This is probably a little mistake. I think what is meant is that no current theory is about the atom are in line with radiation theory. Sommerfeld has made an attempt. His theory permits the calculation of X-rays, linking one attempt by Wien based on Planck's theory with another attempt by Wien based on the theory of electrons. An advantage is also making H in the theory. You have Planck's formula, energy is constant of Planck times the frequency, physically significant. And a disadvantage, it doesn't solve the problem of radiation. This radiation theory are not as satisfactory at all as thermodynamic theories. It's not yet clear how the situation can be overcome. Solutions often come from a tiny different direction than expected. Wien is convinced a complete solution will be found in the future, and it was, of course, with the development of quantum theory. But that was in the future. It was only 1911 at this stage. So it took some years to solve the problems. Here again, you see there are many different ways to make pictures of the Rayleigh genius laws. Here you see another one with frequency and radiance. And here's still another one with wavelength and spectrum. Yeah. If you want to study it, you can better pause the video or follow the link to the source. Here's another one. Unfortunately, this is a strange one because it is not said what is here and what is here. So that's a bit strange. Well, thank you for watching for the moment. This is it. Next time we will go to the year 1912 for the next Nobel Prize in Physics. Again, thank you for watching and maybe till another time.